All right, so we're going to be starting a unit on how chemists keep track of amounts, specifically how we translate amount of atoms, which we know are super tiny, to amounts that we can actually see and measure. And we are going to be using an approach to conversions called dimensional analysis. And it's interesting because the AL was actually there in my original work, but PowerPoint spell checked it. But regardless, we're going to be learning about dimensional analysis. Dimensional analysis is a way to convert between units. It's particularly useful if you have multi-step problems to do, but you can. It's a really useful way of doing conversions. We are going to be using it in chemistry, like I said, to be primarily working with stoichiometry, which is how chemists keep track of amount. But physicists use it a lot as well. At basically anytime there's any kind of derived unit where you have something like miles per hour and you need to convert that to meters per second or vice versa. Things along those lines. As I mentioned in the last slide, dimensional analysis uses conversion factors. And basically conversion factors are written as ratios. Now I know that this example that's shown here, it looks a little confusing right now because it didn't copy over to the app being the way it is in your note packet. But basically what this says is that 1 meter is equivalent to 100 centimeters. And notice that this is set up like a ratio. And you should also note that you can change that around and write it that 100 centimeters is equivalent to 1 meter. So that's why this approach to doing conversions is so useful, because you can set the ratio up or set up the conversion factor the way you need to solve the problem. So it gives you a couple of different ways to write equivalencies. All right, so it makes the most sense to learn about this really by looking at an example. So the example that we're going to do right here is how many seconds are there in 7 days. And what we're going to do with that example is I'm going to show you how to set it up using a format called picket fence. And really, it's called picket fence because a picket fence kind of looks like, and I need to actually get rid of this line right here, but a picket fence looks like this. Okay, so we're going to be putting conversion information in these different boxes, and you can see that you have, looks like fractions, you have numerator, and you have your denominators. Okay, so we need to kind of think about what we've got. Well, so the first piece of information that we're going to put in our picket fence is, what do we know? Well, we know that we have 7 days. Okay, we're going to put that over 1. You always put the information that you know in the first box on the picket fence. So that'll go there. So the next thing we know, well, we know that a day has 24 hours in it. Okay, so there's our first conversion. So when we think about this as the big picture, we're going from days to hours to minutes to seconds. Okay, so that's what we have to do with our conversions. So once we convert days to hours, our next step then is to convert hours to minutes. Well, we know that 1 hour contains 60 minutes. Okay. What you should be noticing is that I'm setting this up so that these units are canceling with each other, and I'll show you more of what that means in a minute. And our last step now is to convert minutes to seconds, and we know that there's 60 seconds in 1 minute. Okay, so what I want you to pay attention to is that there's some things that there's some canceling that happens. Okay, so let's look at that. let's look at the canceling. So you should notice that if you divide days by day, these guys cancel. Hours cancel the same way. Minutes cancel. So there you're left with, your units at the end are seconds. Okay. So how do you solve this? Well, you're going to say 7 times 24 times 60 times 60 divided by 1 times 1 times 1 times 1. So in other words, you take all of the numbers that are in the numerator, so the numerator, and you divide it by all of the numbers that are in the denominator. Okay. So when you do that calculation, 7 times 24 times 60 times 60, you end up getting 4,800 seconds. Okay, so another thing that you can use dimensional analysis for is to convert between metric units. And so that's going to be another way that we use it. You might have wondered why we haven't done any metric conversions to this point this year, or haven't really done many. And this is the reason why I wanted to wait and talk about it in the context of dimensional analysis. So what you see in this table here are some common metric prefixes as well as the base units. I'm going to explain those in a minute. Kind of an interpretation of what that prefix means, and a number that you could use to help you set up conversion factors. All right, so a couple of things that I'm noticing when I'm looking at this. One thing I notice is that when this was copied over, when this copied over, I see that it didn't stay with my Greek font for a couple of things, and it also took numbers out of scientific notation. Okay, so first thing is the prefix micro. You use the Greek letter M, which looks like a U with a tail. It's actually mu. Let's see what else. The other thing is these factors, it took them out of scientific notation, so I'll put it back. Okay, so the first prefix is mega. Mega is a big number, okay? So it's 1 million times larger, the unit that comes in front of it. Then kilo. Kilo is 1,000 times larger. You're probably familiar with kilo. The base unit. Now there's various different base units that we'll be using. Meters are the base unit for length. Liters are the base unit of volume. Grams are the base unit for mass. Seconds are the base unit of time. And moles are the base unit of amount. And as I said, we will be getting into a unit where we learn much more about moles. Joules are the base unit of energy, and pascals are the base unit of pressure. Okay, so base units don't have any kind of prefix next to them. So for example, when you're writing something metric-wise, if I were to write KS, that means kiloseconds, okay? If I were to write mu, M, O-L, that would be micromoles, okay? You could write MJ, that would be millijoules, okay? So the prefixes come in front of the base unit, and they change its value, they multiply it. Okay, so deci is 10 times smaller, centi 100 times smaller, milli 1,000 times smaller, micro 1 million times smaller than the base unit, nano 1 billion times smaller than the base unit, and pico is 1 trillion times smaller than the base unit. All right, so in solving this problem, we're going to do dimensional analysis to convert 0.073 centimeters to micrometers. And I think the way we'll go about doing this one is to go from centimeters to meters to micrometers, okay? Just so that you're aware right here, that is the Greek letter M. And the Greek letter M is micro. All right, so we're going to set up our picket fence just like we did the last time, okay? And again, remember in this first box goes, what do we know from the problem? Okay, so what do I know? I know that I have 0.073 centimeters. Okay. I'm going to put that over 1 again. Okay. So to convert from centimeters to meters, 1 meter is 100 centimeters. And the next thing is, so you should see that, notice that the centimeters cancel there, so that'll put your unit, or that'll give you your answer in meters. The next thing that you need to do is convert from meters to micrometers. So there are 1 times 10 to the 6th micrometers in 1 meter. Okay. So this one looks a little bit different. So to get this conversion correct, you would have to say 0.073 times 1 times 10 to the 6th divided by 100. Remember, you take all of the numbers in the numerator and you divide by the denominator. And again, if we go back and we can look, that our units cancel and our final answer will be in micrometers. When you do that, 0.073 times 1 times 10 to the 6th divided by 100, you get 730 micrometers. And we'll finish up with one last example. So we've got a kind of chemistry related one. So here's our problem. The directions for an experiment, and I do this kind of calculation for you guys as I'm setting up for labs all the time, particularly when I have to make solutions of specific concentrations. I use this dimensional analysis approach. So this could be something that I might have to do, is if I were figuring out if I had enough of something for us to do a particular lab. So the directions for an experiment ask each student to measure out 1.84 grams of copper. We've got some copper on hand, and it's in a spool and it has a mass of 50 grams. So I want to know how many of you guys could actually do the experiment before the spool of copper ran out. So we're going to set up our picket fence. Okay, so what do I know? I know that I have a spool of copper that has a mass of 50 grams. And I also know that one student needs 1.84 grams. Okay? And I want to know how, so if you look at this, you will see that grams cancel, and that leaves me with total number of students. Okay? So when you say 50 times 1 divided by 1.84, you get 27.124. Whoops. Okay, now we're going to round that to 27 because we know we can't have 0.124 students. Okay. So what you should do with this now is come to class prepared to do some examples tomorrow for a do now. Those examples will be turned in and you will be given a formative assessment grade on them.